GFCI ground fault circuit interrupter, and GFEP ground fault equipment protection. Circuits can indeed be susceptible to nuisance tripping due to electromagnetic interference (EMI) from power supply circuits when they are installed in raceways together. This phenomenon occurs because GFCI and GFEP devices are designed to detect very small imbalances in current flow between the hot, or line, conductor and the neutral conductor. Even slight electromagnetic interference can induce a current in the neutral conductor or otherwise disrupt the balanced state that these devices monitor. Several factors contribute to this susceptibility. Firstly, the proximity of the power circuits to the GFCI or GFEP circuits within the raceway is a significant factor. The closer the circuits are, the stronger the electromagnetic field interaction. Secondly, the magnitude of current flowing in the power circuits plays a role. Higher currents generate stronger electromagnetic fields, increasing the likelihood of inducing currents in the GFCI or GFEP circuits. Thirdly, the length of the parallel run of the circuits within the raceway matters. Longer parallel runs increase the opportunity for electromagnetic interference to occur. Fourthly, the type of conductors and raceway material can also influence the amount of EMI. For instance, metallic raceways can provide some shielding, while non-metallic raceways offer minimal shielding. Fifthly, the sensitivity of the GFCI or GFEP device itself is a factor. Some devices are more prone to nuisance tripping than others due to variations in their internal design and manufacturing tolerances. Sixthly, harmonic distortion in the power circuits can exacerbate the problem. Harmonics are additional frequency components in the current waveform that can generate more complex electromagnetic fields. Seventhly, poor grounding practices can also contribute to EMI issues. Inadequate grounding can allow stray currents to flow, increasing the potential for interference. GFCI devices are designed to protect personnel from electrical shock by detecting ground faults. A ground fault occurs when current leaks to ground, such as when someone touches a live wire and provides a path to ground. GFCI devices trip when they detect a difference of approximately 5 milliamps, 5 amps between the current flowing in the hot and neutral conductors. GFEP devices, on the other hand, are designed to protect equipment from damage due to ground faults. They typically trip at a higher current threshold, such as 30 milliamps, 30 amps, or higher, depending on the application and the equipment being protected. The electromagnetic field generated by power circuits carrying significant current can induce a small current in the neutral conductor of the GFCI or GFEP circuit. This induced current, even if it is below the normal operating current, can be enough to create an imbalance that the GFCI or GFEP device interprets as a ground fault, causing it to trip. This is especially true if the GFCI or GFEP device is highly sensitive or if the power circuits are carrying high currents or have significant harmonic distortion. To mitigate the risk of nuisance tripping due to electromagnetic interference, several strategies can be employed. Firstly, physical separation is key. Maintaining as much physical separation as possible between the power circuits and the GFCI or GFEP circuits within the raceway can reduce the electromagnetic coupling. Secondly, using metallic raceways can provide shielding. Metallic raceways act as a Faraday cage, attenuating electromagnetic fields and reducing the amount of interference that reaches the GFCI or GFEP circuits. Thirdly, twisting conductors can help reduce EMI. Twisting the hot and neutral conductors of both the power circuits and the GFCI or GFEP circuits helps to cancel out electromagnetic fields. This is because the electromagnetic fields generated by the individual conductors tend to oppose each other when they are twisted together. Fourthly, using shielded cables can further reduce EMI. Shielded cables have a conductive layer, typically made of copper or aluminum, that surrounds the conductors and is grounded. The shield provides an additional barrier against electromagnetic interference. Fifthly, ensuring proper grounding is essential. A properly grounded electrical system provides a low impedance path for fault currents to flow, reducing the likelihood of stray currents and electromagnetic interference. Sixthly, using line filters can help reduce harmonic distortion. Line filters are designed to attenuate specific frequencies, including harmonics, in the current waveform. Seventhly, adjusting the trip threshold of the GFEP device may be possible in some cases. If the GFEP device is tripping due to EMI, increasing the trip threshold slightly may prevent nuisance tripping without compromising equipment protection. However, it is important to ensure that the trip threshold remains within acceptable limits for the specific equipment being protected. Eighthly, using a GFCI device with a higher trip threshold or a GFCI device that is specifically designed to be less susceptible to EMI may be an option. Some GFCI devices are designed with internal filters or other features that reduce their sensitivity to electromagnetic interference. Ninthly, consider running separate raceways for power circuits and GFCI or GFEP circuits. This is the most effective way to eliminate electromagnetic interference, but it may not always be feasible due to space constraints or cost considerations. Tenthly, carefully inspect all connections. Loose or corroded connections can create high resistance points that generate heat and electromagnetic interference. Tighten all connections and ensure that they are clean and free of corrosion. In addition to these strategies, it is important to follow all applicable electrical codes and standards when installing and maintaining electrical systems. The National Electrical Code (NEC) provides specific requirements for the installation of GFCI and GFEP devices, as well as for the separation of different types of circuits. For example, NEC Section 300.3. C1 addresses the installation of conductors of different systems in the same raceway, cable, or enclosure. It requires that all conductors be insulated for the maximum voltage of any conductor in the raceway, cable, or enclosure. This requirement helps to prevent insulation breakdown and short circuits, which can contribute to EMI. NEC Section 310.15 provides requirements for calculating the ampacity of conductors. The ampacity of a conductor is the maximum current that it can carry continuously under specified conditions of use without exceeding its temperature rating. When conductors are installed in close proximity to each other, such as in a raceway, their ampacity may need to be derated to account for the effects of mutual heating. This derating can affect the amount of current that can be carried in the power circuits, which in turn can affect the amount of electromagnetic interference generated. NEC Section 250 provides requirements for grounding and bonding. Proper grounding and bonding are essential for electrical safety and for reducing the risk of electromagnetic interference. A properly grounded electrical system provides a low impedance path for fault currents to flow, which helps to protect people and equipment from electrical shock. It also helps to reduce the amount of stray currents and electromagnetic interference that can be generated. In addition to the NEC, other standards such as those published by the Institute of Electrical and Electronics Engineers (IEE) provide guidance on electromagnetic compatibility (EMC). EMC is the ability of electrical equipment to function properly in its electromagnetic environment without causing interference to other equipment. EMC standards provide requirements for the design and testing of electrical equipment to ensure that it meets certain levels of immunity to electromagnetic interference. When troubleshooting nuisance tripping of GFCI or GFEP circuits, it is important to follow a systematic approach. Firstly, verify that the GFCI or GFEP device is properly installed and wired. Check the connections to ensure that they are tight and that the device is properly grounded. Secondly, measure the voltage and current in the circuit to ensure that they are within acceptable limits. Overvoltage or overcurrent conditions can cause nuisance tripping. Thirdly, check for any loose or corroded connections in the circuit. Loose connections can create high resistance points that generate heat and electromagnetic interference. Fourthly, use an electromagnetic field meter to measure the amount of EMI in the vicinity of the GFCI or GFEP device. This can help to identify potential sources of interference. Fifthly, try temporarily disconnecting any nearby equipment that may be generating EMI to see if this eliminates the nuisance tripping. Sixthly, if the nuisance tripping persists, consider replacing the GFCI or GFEP device with a device that is specifically designed to be less susceptible to EMI. Seventhly, consult with a qualified electrician or electrical engineer to help troubleshoot the problem. They can perform more advanced testing and analysis to identify the root cause of the nuisance tripping and recommend appropriate solutions. Understanding the principles of electromagnetic interference and how it can affect GFCI and GFEP circuits is essential for ensuring the safety and reliability of electrical systems. By following the strategies outlined above, it is possible to mitigate the risk of nuisance tripping and ensure that these important safety devices function properly. It's also important to note that certain types of loads, such as variable frequency drives, VFDs, and switching power supplies, can generate significant amounts of harmonic distortion. Harmonic distortion can exacerbate EMI problems and increase the likelihood of nuisance tripping. In these cases, it may be necessary to install harmonic filters to reduce the amount of harmonic distortion in the electrical system. These filters are designed to attenuate specific harmonic frequencies, reducing the impact on sensitive electronic equipment. The location of the GFCI or GFEP device within the electrical system can also affect its susceptibility to EMI. For example, a GFCI device that is located close to a source of EMI, such as a VFD, may be more prone to nuisance tripping than a GFCI device that is located further away. In these cases, it may be necessary to relocate the GFCI device to a less noisy location. Another factor to consider is the type of wiring method used in the electrical system. Wiring methods that provide better shielding, such as metal conduit or shielded cables, can help to reduce the amount of EMI that reaches the GFCI or GFEP device. In contrast, wiring methods that provide minimal shielding, such as non-metallic conduit or open wiring, may increase the susceptibility to EMI. When working with electrical systems, it is important to always follow safe work practices. De-energize the circuit before working on it, and use appropriate personal protective equipment (PPE), such as safety glasses, gloves, and insulated tools. It is also important to have a thorough understanding of the electrical codes and standards that apply to the specific installation. These codes and standards are designed to ensure the safety and reliability of electrical systems, and they provide guidance on proper installation, grounding, and bonding techniques. By following these guidelines, it is possible to minimize the risk of electrical shock and other hazards. In summary, GFCI and GFEP circuits can be susceptible to nuisance tripping due to electromagnetic interference from power supply circuits. Several factors can contribute to this susceptibility, including the proximity of the circuits, the magnitude of current flowing in the power circuits, the length of the parallel run, the type of conductors and raceway material, the sensitivity of the GFCI or GFEP device, harmonic distortion, and poor grounding practices. To mitigate the risk of nuisance tripping, several strategies can be employed, including physical separation, using metallic raceways, twisting conductors, using shielded cables, ensuring proper grounding, using line filters, adjusting the trip threshold of the GFEP device, using a GFCI device with a high trip threshold or one designed to be less susceptible to EMI, running separate raceways, and carefully inspecting all connections. By understanding the principles of electromagnetic interference and following these strategies, it is possible to ensure the safety and reliability of electrical systems.